Hello, this is Eva Amsen welcoming you to this Bite-Size Bio webinar, which today is sponsored by MilliporeSigma. MilliporeSigma is a leading supplier to the global life science industry with solutions and services for research, development, and production of biotechnology and pharmaceutical drug therapies. Today's presentation is titled Contamination and Recovery of PFAS in Analytical Methods Requiring Filter Membranes, and it's being presented by Lindsay Loiseau, Senior Scientist at MilliporeSigma. Lindsay received a PhD in Chemical Engineering in 2017 and an MBA certificate in Entrepreneurship in 2018 from Worcester Polytechnic Institute, where her thesis focused on the design and functional analysis of new antimicrobial therapeutics. At MilliporeSigma, she is a Senior Scientist in Analytical Sciences, focused on developing new products related to cut-disc membrane filters, non-sterile syringe filter devices, filtration hardware, and smart lab products and software. She is also part of a team responsible for technical content creation and developing applications relating to microfiltration products. As always, we will have a question and answer session after the presentation, so please type any questions you have into the questions box, which appears on the top right panel of your screen, and I'll put them to Lindsay at the end. So now, over to you, Lindsay, for the presentation.
Good morning, good afternoon, and good evening, everyone. My name is Lindsay Loiseau, and I'm a Senior Scientist at MilliporeSigma based in Burlington, Massachusetts. I'm focused on new product development and applications development for cut disc membrane filters, as well as non-sterile Millex syringe filters and all the hardware that goes with them. And today I'm here to talk about some of the work I've done in the environmental area in the last few years, titled Contamination and Recovery of PFAS in Analytical Methods Requiring Filter Membranes. Before I start, I like to read the following. MilliporeSigma is the US and Canada life science business of Merck KGaA, Darmstadt, Germany. And also before I start, I want to mention that my role in studying filtration consumables for PFAS is only a small portion of a much bigger effort going on at MilliporeSigma across all of our different brands to support the entire sample preparation workflow for analytical methods involving PFAS. So that includes anywhere from sample collection all the way through analysis, including our MilliQ water purification systems, labware, and sample containers, SPE cartridges, XAD tubes, and other consumables in addition to filters, as well as certified reference materials and all the way up through columns. So if you have any questions about any of these different types of products or are in need of technical content, please check out our website or the QR code here to take a look at our content arranged by method for more information. And now I'll dive right in. So probably a lot of you have heard of PFAS, or per and polyfluoroalkylated substances. This is a broad term of a class of over 4,000 very stable fluorinated chemicals, and this amount is only growing. Historically, these PFAS molecules have been used in the manufacture of a variety of different products, such as non-stick coatings on your pans, or firefighting foam, and anything that is waterproofed. So these great properties and chemical stability of PFAS-based molecules has unfortunately caused them to be pretty ubiquitous in the environment, giving them the name of forever chemicals. And there's been mounting evidence in recent years of their negative potential health impacts to humans and aquaculture. And there's been, because of that, an increased need for analytical testing in matrices all the way from direct routes like drinking water and foods, all the way through non-potable waters, environmental waters, and beyond. And this has been catalyzed by a large amount of regulations looking at different advisory levels, both in the United States and on a global scale. And this has been catalyzed by different meetings such as the Stockholm Convention, or plans mapped out by agencies such as the EPA, which outline that analytical testing for PFAS is not going to go anywhere anytime soon. as I mentioned, a lot of these regulations have catalyzed the need for analytical methods. And likewise, analytical methods for detecting PFAS in a variety of different matrices have been released at an unprecedented pace. And you can probably see that just by the dates that are listed here on this snapshot of the regulatory landscape for PFAS, starting at the earliest in 2017 and heading all the way up to the EPA Draft 1633, which was recently updated a little over a month ago. What you'll notice from this regulatory landscape is that almost all of these are exclusively LC-MS-based methods, and almost all of them include predominantly some type of sample preparation, such as SPE or filtration. And there's also a little bit of a trend starting out with drinking water with EPA 537.1 and 533. But now the focus has shifted to those types of matrices that have higher degrees of particulates, such as wastewater, sludges, leachates, foods, biosolids, tissues. And with that, there's been an increased focus on what kind of sample prep might be appropriate. So this is that regulatory landscape that is focused in on those that are filtration relevant, given that my focus is in filtration. And it also has these methods required filtration requirements. So there are a variety of different requirements for a filter for a PFAS analytical method. And you can see that just by the list here. They're anywhere from syringe filters to cut disc membrane filters that you would handle with forceps. And there are many different materials that are being suggested. So you have polypropylene, for instance, glass fiber, which is GFF, and nylon. So there are a bunch of different form factors as well as the types of materials. And in this talk, I was interested in exploring and asking the question, which syringe filters or cut disc membranes might be best for PFAS analytical applications. Now, with any method, there are always concerns regarding consumables that might come in contact with your sample. And PFAS methods are no different than this. The two major concerns are contamination and absorption. So first of all, contamination. That's basically where a consumable might be already contaminated with the analyte of interest. In the case of PFAS, that indicates fluorinated-based compounds where maybe a consumable was manufactured either with a fluorinated-based compound or in an environment that has fluorinated compounds. An example would be using a Teflon-lined container for sample collection. The other concern is adsorption, nonspecific adsorption of any of your analytes of interest, which in this case are PFAS compounds, non-specifically onto the surface of a consumable. That includes for filters, the filtration media. This can actually lead to potential low recoveries. An example of that has been seen in the literature for glass containers, where it's said that different types of PFAS compounds can non-specifically bind or absorb onto glass surfaces and lead to lower recoveries. Now, that's been debated in literature, but it's still a major concern for many of these methods. And obviously, with PFAS in specifically, you want to avoid fluorinated-based compounds, which I'll talk about in a little bit. Because mostly we've found that, and I'll show in this talk, that contamination of PFAS might not always be obvious if it's coming from a filter. Now, because of these concerns, it's been suggested in a lot of cases that if you have a clean sample, one that doesn't have particulates, it's advised that less is more. Dilute and shoot, for example, skipping filtration or sample prep altogether is suggested. So if that's the case, then why would you use a filter or a SPE cartridge or something to prep your sample in the first place? Now, in the case of higher particulate samples, or those samples that have particles that could potentially get through and into your instrument, it has been shown that data quality coming from these types of samples can be significantly reduced if the proper sample preparation steps aren't taken. So filtration in that respect is one of the easiest and cheapest ways to bring a sample to an amenable format for analysis. And if anyone's seen any chromatograms coming from PFAS analytical methods, they're very, very busy. And if that's the case, then adding any unnecessary peaks from particulates introduced into the system could significantly reduce the data quality and analysis. Second is that we've shown in the past that for mobile phase, or the sample that or solution that is constantly contacting your chromatographic column, can introduce increases of back pressure for a column if it has particulate matter in it. So what I'm showing here is actually back pressure in PSI of a column versus time that a mobile phase is being flowed through. And there are two cases here. The first case is the light blue and the pink, where a low retention filter, meaning that a filter that introduces more particles into the system, was used on the mobile phase, versus the green and the dark blue, where a high retention particle filter greater than 98% was used to filter the mobile phase. And you can see from here that the back pressure changed almost immediately when using a mobile phase that had higher particulates in it. And what that indicates is that the chromatography column is getting closer and closer to being clogged, which will cause issues with not only the lifetime of the column, but also can potentially damage instruments and lower the quality of data. Now, that's true for mobile phase, but we also asked the question, what about the sample? And we found much of the same story, is that even though a sample as low as 10 microliters of an injection might be very, very little exposed to the column, having undissolved particles in a sample can actually cause a similar change in back pressure. So here is a similar looking plot where we're showing back pressure of a column versus injection number of 10 microliter volume injections. And the pink here is an unfiltered sample with particulates being flown through the system, whereas the yellow here is a membrane with poor retention, similar to the plot on the left with the light blue and the pink. And the green and the blue and the purple symbols below are those samples that were filtered with membranes that have good retention, greater than 99 or 98%. And what we're showing here is that only with 10 microliters of a sample injection, there can be a significant increase in back pressure, leading to the lifetime of the column being significantly shortened. So in the case of the membrane with poor retention, it was only about 71 injections before the back pressure reached an unsafe level. And when the unfiltered, it was only 39. So not only can the mobile phase with particulates damage your column, but also a sample as low as 10 microliters. So that's why you might want to filter. So in the first part of the study, we focused on looking at different syringe filters within the scope of these PFAS analytical methods. And our focus was to first look at contamination. Are these filters adding to the problem? In terms of PFAS compounds and contamination. And secondary, we wanted to look at the absorption behavior of different types of PFAS compounds and C13 labeled standards onto different filter media. So for this study, we had a lot of different choices, and you can see images here. Unfortunately for us, PVDF, or polyvinylidene fluoride, and PTFE, polytetrafluoroethylene, are two of our most commonly suggested sample prep filters due to their low binding properties, their great retention of particles, and their really stable chemical durability. But unfortunately, these two filters are fluorinated. So for PFAS methods, they're not the most ideal, and we should try and look at alternatives. So what I looked at within the scope of these studies were our polyether sulfone, or PES membranes. Now, these are an asymmetric membrane, which is unique. In this case, they're appropriate for high particulate matrices because they have larger pores toward the retentate side and smaller pores toward the filtrate side. And so you can see that in the cross-section picture. That allows them to have higher flows for the same higher particulate samples than most other membrane filters. Secondly, we wanted to choose, I wanted to choose nylon because nylon's very commonly used in HPLC-based methods. It's very chemically compatible and suggested for use for some of these membranes, as we've already learned. And additionally, I wanted to study our nylon HPF, which is the picture on the bottom right. That stands for high particulate filter, and basically what it is a nylon membrane coupled to a glass fiber pre-filter. That also, similar to PES, allows for higher flows and lower chances of clogging, but I also wanted to do a little bit of a deep dive on non-specific absorption due to glass fiber versus nylon, and so that's why we chose that one. So in order to start this study, we actually collaborated with SGS in Orlando, Florida, to develop a method that analyzed the contamination of our syringe filters. And you can see a list just within the image on the left of which syringe filters we chose. And we did that according to a modified version of EPA 537.1, where we spiked water samples with C13 labeled standards, filtered them, and then concentrated everything coming off of that filter and analyzed for PFAS contamination. Now, you're probably wondering, well, EPA 537.1 wasn't on your filtration list in terms of the methods, and that's because it's drinking water. So the reason why we used EPA 537.1 in this case was because the drinking water method provided a very, very clean sample matrix in order for us to isolate the filters as much as possible to determine contamination levels. And here are the results that we found coming off of those filters. So here, they're actually, all the different compounds here are listed by their RL, or their reporting limits. So they're just clumped together. But overall, what we found was there was non-detectable levels of all of these PFAS compounds in all of the syringe filters, lots, and number of devices that we tested. So we found non-detect across the board, both above the RL, the reporting limit, as well as the MDL, or the method detection limit. So that indicates that our samples, or at least these particular filters, were clean of PFAS and appropriate to be used with this method. At the same time, I did want to look at recovery values, and we used the C13 standards that we spiked the samples with in order to do so. So here you're looking at a snapshot of the recovery of a few different C13 labeled standards that we tested within this method. And overall, what we found was that for all of the compounds, no matter what we tested, and no matter what's shown here, the recoveries landed within the acceptable QC range, which is indicated by the purple range here. But what's interesting in the nuanced information and consistent across the board was that PES, or polyether sulfone membranes, had samples that had higher recovery overall than anything that had nylon in it. Now, this has actually been observed before in aqueous matrices for nylon specifically. In general, nylon tends to be more chemically sticky when interacting with different kinds of molecules. And in this case, in water, it is for PFAS samples. We've also seen this for other molecules such as proteins, and literature has also reported this for nylon. So this was unsurprising. After showing a lack of contamination in water, we wanted to turn around and look at a more relevant to filtration method, EPA Draft 1633, which has higher particulate matrices and calls out for a 0.2 micron nylon syringe filter. This method is primarily in methanol. And with SGS, we designed a similar study for EPA 1633 as we had tested for EPA 537.1. So very, very analogous methods. Now, for EPA 1633, there is a slight difference in the upfront sample preparation methods and extraction methods, depending on which matrix for EPA 1633 that you start out with. So what we did with SGS was look at the workflow and pick out the portion at which filtration was relevant. So in the image on the left here, you see the little star. That's just highlighting the place along the workflow where filtration was consistent across all three matrices. And we zoomed in on that method in order, once again, to isolate the filter and investigate contamination potential. So what we did was we spiked methanol samples with C13 standards and then looked at anything coming off the filter using LCMS analysis. A major difference between this study and the previous is that the number of analytes is expanded. So we looked at 40 different types of compounds here for PFAS, and the filtrate primarily was methanol. And here are the results that we found for this. So once again, I'm organizing all of this by the reporting limits just to make this table a little bit easier to digest. But the most important part is that going across the top are the different filters we investigated. And you see that there are NDs for everything listed on this table. Now, in this particular study, we actually we tested another nylon syringe filter from a different manufacturer. So that's called manufacturer 5 here. And we really just wanted to use that to benchmark our filter's performance against something else that's in the market. And you can see again, everything is non-detect. If you have questions about the specific MDLs, which were different depending on the compounds, please let me know or take a look at our tech article. Now, one thing that we did notice within our testing here was within the nylon HPF, that was that glass fiber and nylon filter itself. One of the lots out of the 2 lots we tested, and one of the device out of the 3 devices we tested, did actually identify some levels of PFCAs, which are the carboxylic acids. And you're seeing that here just highlighted, kind of blown up in blue color. The one thing I wanted to note is that all of these values here are actually lower than the RL, or the reporting limit, and higher than the MDL. What that indicates is that in general, this concentration that's considered a hit is estimated, because between the MDL and RL, there's difficulties in certainty and quantification. So that's the first thing. The second thing is that we actually threw in another device, a 4th device, just to see if this was a consistent problem for nylon HPF, or if it maybe was due to something else within the method. And everything we saw for this 4th device was non-detect. So within that, we can't say for sure whether or not this contamination is due to the device itself, the processing parameters within the method, uncertainty, or anything else. So that's something to just keep in mind as we move forward through these tests. We also looked at the recoveries of those C13 labeled standards for the different filters. And the most important thing here is, once again, there's a snapshot of these C13 labeled standards, but you'll notice that compared to the PES or the EPA 537.1 data, is that the PES samples, or the yellow in this case, is actually now at the same level as all of the nylon, both from that competitor filter as well as ours. And they're all about at 100% recovery. What this indicates is that in methanol, the filters have similar recoveries, and that's likely due to the idea that PFAS have a higher solubility within methanol than they do with water. So there's some degree of a rinsing effect that methanol has when in contact with nylon syringe filters. Another question that we get quite often for our syringe filter devices is the question about diameter of the filter. So we actually offer a 33 millimeter diameter versus many other devices that are on the market of 25 millimeter sizes. And so we get this question about whether that causes issues with the filtration itself. Now, there is a major difference, or at least a difference, in holdup volume. That's the amount of liquid that gets held up within the filter, and that's simply due to the higher surface area. But we wanted to know if that made a difference for binding analyte, specifically within PFAS here. And we worked with Alpha Analytical to study this a little bit, where we ran the entirety of EPA 1633 with aqueous matrix, spiked with 2 levels of reference standards. So we have a low level, which is the plot on the top, and a mid level, which is the plot on the bottom, next to C13 labeled standards. And we looked at the recovery of those native compounds head to head with our 33 millimeter and a competitor of 25 millimeters. And these two plots actually calculate the average loss of analyte. What that means essentially is the difference between what we spiked with and what we ended up with, normalized to the surface area or per centimeter squared of the different compounds. Now, the most important thing or takeaway from this is the blue versus the pink here. You can see that across the board for this snapshot, the blue and the pink aren't considerably different. What that means is that the loss of analyte was about the same, and in some cases, actually less for a 33 millimeter device than it was for the 25. So there were similar overall losses of analyte in the case of both spikes. And what this really means is that larger filtration areas don't necessarily lead to a larger analyte loss, and that not all nylon behaves chemically the same depending on the manufacturer that you get it from. Now, everything up till now has been focused around syringe filters because this is the most common form factor. But we get a lot of questions about mobile phase filtration, which requires a cut disc membrane type filter. So given that we typically recommend PTFE for this, which is not great for PFAS methods, we wanted to look at potential alternatives. And our polypropylene, both hydrophilic and hydrophobic wettabilities depicted here, were potentially a good alternative. And that's because they have a lot of similar properties to PTFE. So this image on the left is just showing intensity versus retention time of chemical extractables, essentially, for polypropylene, the top two lines, versus PTFE, the green line, and a couple of controls in basic methanol. So basically anything here that shows a spike different than that of the blanks could indicate a chemical extractable coming off the membrane. What this shows is very similar chemical compatibility properties, at least in basic methanol, for polypropylene versus PTFE. They're very similar. And overall, there's similar retention of particles in air and liquid, a pretty high stability to heating, and polypropylene is actually suggested for use in many of the PFAS analytical methods. So what we wanted to do was actually ask the question whether or not these polypropylene membrane filters could be suitable for PFAS analytical methods by doing much of what we already did. Now, because these are in the cut disc form factor, we had to bring them to an amenable form factor in order to test using EPA 537 and 1633. And the way we did that was actually by using this cute little device called Swinex. This is a reusable device that can turn any cut disc membrane filter into a syringe filter on demand. And you can see that from the image below. You just apply a syringe barrel onto the edge of the Swinex and you filter just as any other syringe filter. And we used this form factor to test first with 537.1, which was in water. Here are the results for hydrophobic and hydrophilic polypropylene of two different pore sizes for EPA 537.1 in water. And what you'll see immediately from this is that we showed non-detectable levels of any of these PFAS compounds above the RL and the MDL in EPA 537.1. There is one notable footnote here under the perfluoroalkyl carboxylic acids, specifically the long chain ones for hydrophobic polypropylene. This footnote indicates that there were low recoveries of the C13 standards for those particular long chain PFCAs, and I'll show a little bit more of that data later. This next slide shows testing hydrophilic polypropylene membranes using EPA Draft 1633 in Swinex devices. Now here we used 0.2 hydrophilic polypropylene only. We didn't use hydrophobic or anything because this is the most comparable to that 0.2 micron nylon that's called out in EPA 1633. So we wanted to use the most relevant filter for the job. And across the board here, for any of those 40 compounds that were analyzed, we didn't detect any levels of PFAS contamination above both the RL and the MDL. So that was really, really good. Now, I mentioned we had some troubles with recovery, specifically looking at the phobic polypropylene membranes. So what you're looking at here is just a snapshot of the PFCA's C13 labeled standards in water for both the hydrophilic, which is dark blue, and the hydrophobic polypropylene, which is light blue. And you can see for the long chain perfluoroalkyl carboxylic acids, all the way to the right of the plot, you had significant differences in the amount of recovery that you got using a philic polypropylene versus a phobic polypropylene in water. So overall, it was lower for hydrophobic polypropylene. And that could be due to these PFAS compounds being very bulky, hydrophobic interactions with the surface of the membrane filter, and of course, solubility within water. So philic polypropylene actually behaved very similar to PES, if you remember that data. On the flip side, hydrophilic polypropylene actually performed very similarly overall in both water and methanol, again, like PES. So here are all of the C13 labeled standards and their recoveries for philic polypropylene in both water in blue and methanol in green. And you can see that there's pretty few differences across the board. Of course, with long chain PFAS, there are still problems because even philic polypropylene is relatively phobic. So you do have some phobic interactions happening there, but overall there's very few differences in water and methanol. So that rinsing effect isn't seen for hydrophilic polypropylene like it is for hydrophilic nylon. Thus, we recommend that, especially for any water-based methods, you use hydrophilic polypropylene for filtration in PFAS analytical testing. Next, I'm switching gears to a whole different matrix. The EPA strategic roadmap includes an enhanced focus on air matrices in the upcoming years. And so far, the only method that is an air-based method is OTM 45, which requires a cut disc membrane filter up front as a particulate fraction filter. Now, anyone who is familiar with OTM 45 knows that it's a monster of a method. There are 7 different fractions on a sampling train, which is very, very large, and each fraction is extracted and analyzed sort of separately on both the front half and the back half of this extraction. Now, I wanted to focus in on the first fraction, which is the filter for collecting particulate phase. And these are some of the requirements for this particulate phase filter. I matched our closest glass fiber filter to this method, and it was our AP40 glass fiber depth filter. Now, this is actually used for a lot of hot gas-based filtration and similar stack testing applications, as well as different, EPA-based methods like total suspended solids. And our goal was to really look at whether or not this AP40 glass fiber filter was suitable to be used for OTM 45. We collaborated with Eurofins Knoxville for this particular study to develop a method that I'm depicting here, which mimics the steps used for both cleaning and front half extraction of all the consumables within OTM 45, which is a pretty rigorous method. So here you can see there's a sample, there are soaks of the membrane filters, and then the extraction itself is several hours long. So it's a pretty demanding method on your consumables. Now, within this method, what we did was we skipped the sampling train portion, which is in the middle here. The reason for that is very similar to why we used the drinking water method for EPA 537.1 to look at contamination, because what we really wanted to do was isolate that glass fiber filter and anything that was coming off that specifically during cleaning and front half extraction. So we've typically, we've actually tested these filters in a subsequent study that's actually just wrapping up. And we have found some pretty favorable results for glass fiber discs out in the field for stack sampling as well. But here I wanted to show 90 millimeter AP40 glass fiber discs head to head with another competitor that's used for these types of stack testings within OTM 45. And here you're seeing the results. Now, once again, they're organized by RL, and keep in mind that this is actually even more compounds than EPA 1633 has. And we saw 3 hits overall for our filters, which we saw pretty consistently. And we actually, in a lot of cases, saw it with the competitor filter that I'm also pointing out here. So for perfluorohexanoic acid and PFOS, or perfluorooctane sulfonic acid, the hits were higher than the MDL, but lower than the RL. What that means is there's some uncertainty in quantifying. Further, PFOS was also seen in the competitor filter at very similar levels. Now with perfluoroheptanoic acid, the level was above the RL for all the filters seen. So not just the competitor, but also ours as well. And both lots we tested. It was fairly consistent across the different lots. And I want to note here that for both the competitor and for our filters, these results were pooled, meaning a pooled result from a group of 3 different filters. Thus, one could make the assumption that if each membrane is equally contaminated, then the individual contamination of PFAS concentration is actually lower than that RL. But here it's fairly repeatable. And you can come to expect sort of from all these glass fibers that PFHPA will be there. It's hard to speculate where this is coming from, given that this is glass fiber. But given the consistency and the appearance of this contamination, even through that rigorous cleaning step, it's likely that these compounds will always be showing within the scope of OTM 45, and that anyone doing this method should be cognizant of that. I don't want to go too much into recovery here, but this is the recovery of all the C13 standards for OTM 45 for both our AP40 filters as well as a competitor filter. And what I want to point out is that most recoveries were pretty good, ranging from 80 to 100%. You can see the acceptable QC range outlined by these dotted lines here. And I do want to note that there are some that are sort of high, right? And there are some that are sort of low. And the reason for that is that there's no single method that's appropriate for all the different PFAS compounds of interest. That includes polar, non-polar, volatile, or semi-volatile. And this is actually reflected in a lot of these recoveries. So there are actually many other methods being drafted right now related to OTM 45 that'll focus on specific groups of PFAS that have chemical similarities. And that way the recoveries for those won't be necessarily the recoveries of those won't necessarily be as troublesome as they are within this method. There's no one method to rule them all, so to speak. Within the scope of our filters here showing some pretty high recoveries, it just indicates that for some of these compounds, specifically, the more polar or more volatile ones, that the recoveries aren't necessarily due to the filter material, but potentially that of method parameters. This brings me sort of to the end of what I wanted to show you today. So just in summary, we looked at a lot of different types of filters, both syringe filter and cut disc filter formats. We also looked at our little Swinex devices for a lot of the cut disc membrane filters. And we investigated their suitability for sample prep for PFAS analytical methods. Now that's both prep of the sample as well as mobile phase. And we looked at both aqueous and methanol-based filtrates using EPA 537.1 as well as EPA 1633. We looked at extractables coming off of the membrane. So are we adding to the problem? And we also looked at internal standard as well as native compounds recoveries to determine adsorption or non-specific adsorption onto filter media and whether or not that would be an issue. And we found that many of our filters were indeed suitable for either sample or mobile phase filtration and sample prep within the scope of aqueous via EPA 537.1 or methanol-based methods such as EPA Draft 1633. We also looked at air, the OTM 45, and we looked at glass fiber suitability for that particular method. A few key takeaways that we can bring from these results here is that PES and hydrophilic polypropylene, show very similar recoveries regardless of whether you're filtering water or methanol, while nylon and nylon HPF and hydrophobic polypropylene did not show that same trend. There were differences in the amount of binding or nonspecific binding that you could get within these different matrices. We found, however, that for nylon, rinsing it with methanol desorbed a lot of PFAS compounds. So even if you're using nylon for water-based methods, it suggested that a nice methanol rinse should be able to allow for increased recoveries. Larger filtration areas, such as 33 millimeter versus 25 millimeters, didn't lead necessarily to a loss of any additional analyte that you would expect, while the holdup volumes, of course, were different. And additionally, that study also showed that not all nylon is necessarily the same. So definitely get to know your consumable as you're using these methods. And then we also showed that polypropylene, specifically hydrophilic polypropylene, but also hydrophobic, is a really good alternative to PTFE for sample prep and mobile phase prep in a lot of cases. Now, with that, that brings me to the end. And I want to thank all of you for listening today, or anyone who's listening in on the recording. And my contact information is listed here if you have any questions, but I'll be happy to take them now. Thank you so much.
Thank you, Lindsay. That was an excellent presentation of a very comprehensive study. We have a few questions from the audience. If anyone else has a question, please feel free to post this in the questions box that appears on the top right of your screen. So the first question is, where can I find the polypropylene syringe filters for the ASTM methods that you mentioned?
Yeah, so thank you for asking this. This is sort of a complicated answer because the ASTM methods were actually drafted and written in, I believe it was before 2019. And in 2019, actually a key polypropylene syringe filter, including the one that was called out in the method, was discontinued. So that became a challenge for a lot of analytical testing labs to find the right filter for the job. Luckily, the filter that's called out is actually in a footnote. So it's basically a suggestion for use within the method itself. And there's also kind of a good fail-safe written in where an equivalent membrane could also be used. So what that means is that if any other hydrophilic polypropylenes come along, then those are definitely appropriate. We've also gotten many of the testing labs. They've actually told us that, I'm using a phobic polypropylene syringe filter. And that's definitely found to be suitable in a lot of the methods. But as I mentioned, one has to be careful about recoveries when using a phobic one. Additionally, nylon is perfectly suitable for these methods as long as it's validated properly by the analytical testing lab.
Great, thanks. And the next question, do I need to use a specific syringe filter that's called out in a particular method?
Yeah. So I think I kind of touched on it a little bit with polypropylene, right? There definitely are labs that have validated certain filters in-house. So, the reason for this presentation was really to just give additional options for those labs looking for the right filter for the job. And in almost all of these methods, the idea of equivalency is sort of becoming a consistent phrasing. So in case the filter that you don't have is something that's called out, then you can definitely revalidate something else, as long as the chemical, there are a lot of other reasons why you might choose a filter, as we've mentioned, like particulate retention, stability to heating, things of that nature. So as long as those match within the method, then they definitely can be used. Lastly, I did want to mention, I forgot to mention with the question before, that it's definitely, if you find the right cut disc membrane, you can also put it in the right form factor by using instruments like Swinex. And this study showed that Swinex is actually amenable to a lot of the methods as well, just because it doesn't have contamination.
Great, thanks. Here's a question that just came in. Some studies suggest polystyrene and some suggest amber glass as they have less absorption over time. adsorption, sorry. What material do you suggest to use to contain samples for PFAS?
Yeah, that question comes in a lot about what containers are right. So I didn't personally test any sample containers within this study, but I can comment that there's been a lot of mixed results on different kinds of glass. We didn't really see a significant challenge with our glass fiber membranes in terms of non-specific absorption, but it's definitely possible with the polarity that you see with glass containers. Polystyrene, I would be a little careful just based off of chemical compatibility at that point. If it's in some kind of if you're using samples that are in methanol or in methylene chloride, and you put it in polystyrene, there could be some issues there. You could get chemical extractables at that point, not necessarily PFAS. And lastly, I definitely have heard a lot of studies about questions on fluorinated containers themselves. So sometimes manufacturers won't necessarily say if a container is fluorinated on the inside or not, just so that it could be nonstick and things like that. So that's definitely something also to be aware of. But a lot of sample containers are kind of tested in a very similar way to what we did here. So I definitely suggest that if you're looking at polystyrene and amber glass.
Great, thanks.
Mhm.
I've got one question left, unless we have anything else coming in. For the OTM45 testing that you showed, wouldn't soaking in methylene chloride damage the glass fiber membrane and compromise the performance?
Yeah, so we didn't test that in the results that I showed here, but I can actually comment on two things. The first thing is that, it definitely is a harsh treatment. I wouldn't throw just any filter into that environment. I know a lot of people will use quartz fiber as well. Quartz and glass are both really hardy cut disc membrane types. And can really stand up to a lot of even really harsh chemical treatments. So that's one thing. The other thing is that we did see some contamination. So it's very possible that these depth filters were manufactured with something or an environment that might have been contaminated, and the methylene chloride really extracted it and really pulled out all of that stuff. So it's potential there. The second thing I wanted to comment on is definitely something I didn't talk about, but I did mention that we took those glass fibers and actually brought them out to the field and did some stack testing afterward. So that data I haven't published yet, but definitely I can say that a lot of the results seemed really, really positive, and very comparable to what other stack testing companies use in terms of their glass fiber particulate filters. So there was similar performance overall, but definitely, yes, very harsh. Not all membranes would be able to live up to those soaking conditions and extract. Yeah.
Well, thanks very much. That brings us to the end of the webinar. So thank you again, Lindsay, for a very illuminating presentation and a great discussion. And thanks to our sponsor, Millipore Sigma. And finally, thanks to you, the audience, for taking the time to attend and listen in. So until next time, good luck in your research, and goodbye from all of us at Millipore Sigma and Bite Size Bio.